All right. Well, thanks everyone for being here on this Thursday for the Western U.S. Paleoglaciers Speaker Series. We're fortunate to have two speakers on our schedule again this week. We have Jordan Dahle from North Dakota State University and Aaron Barth from Rowan University, and they'll be presenting in that order. It's actually a great pleasure for me to be able to introduce Jordan Dahle. Jordan is a PhD candidate at North Dakota State University in the environmental science program, and I'm serving her as her dissertation advisor. So Jordan graduated from the University of Minnesota Morris. I have to admit, I didn't write down your bio, Jordan. Sorry about that. So I don't remember what year that was, but I'll say 2019. Was that right? Mm-hmm. Oh, good. All right. And then Jordan completed a master's degree at North Dakota State University that involved a few different topics. She was looking at the glacial record, the Pleistocene glacial record in the Great Basin region of the Western U.S., and that's the topic that she'll be presenting on today. Jordan is working on her PhD now. That involves continued work on Pleistocene chronologies in the West. She's been working so far with Keith Brugger and with me on developing an ice recession chronology in the Taylor Valley in the Sawatch Range and the Elk Range. And we'll be hearing about that sometime in the future, I suppose, Jordan. So with that, we'll let Jordan share her screen and take it away.
Thank you, Ben. There we go. So yeah, this is going to be a bit of work from my master's. It's kind of a compilation of available data from myself and Ben and a bunch of other researchers who have worked throughout the Great Basin. And a few of you may have already heard bits and pieces of this presentation, so bear with me. Also, I'm getting over being sick, so my voice might crack a few times while I'm presenting. Please bear with me. We've got references here on the right to all of the work that has been done by the wonderful people who have collected this data, and then a map on the left showing the ranges we're going to be talking about with the maximum LGM extents of the glaciers in white and the high stand extents of the lakes in blue. We'll talk first about glaciers and then a little bit about pluvial lakes and climate implications. So this is all of the data that we're going to be looking at. We'll mostly be looking at ridgeline plots, density ridgeline plots. This is all of the data, but we're not going to look at all of it for very long. We're going to cut out all of the pre-LGM data here pretty quickly. But I want to show you what is available within the Great Basin because it's a really interesting area to look at glacial chronologies. So there is a bit of pre-LGM data available, but it's more sparse and we have to deal with a lot of surface exposure and incomplete exposure histories and things that make the information a little bit harder to interpret and make it something that can't really be included easily with what we're going to be talking about today. So we won't spend a lot of time looking at that. What we do care about are these LGM age surfaces. So here are all of the ridges representing dated surfaces by range within the Great Basin. We have ages spanning from around 10,000 years ago to almost 30,000 years ago. And it's a little bit muddy and hard to interpret at all if we don't classify these in a nice, clean manner. So what we decided to do was classify these into 5 groups. The first being pre-LGM, which we are being very general here and just grouping everything that is before what is obviously the LGM terminal moraine into this broad pre-LGM group. Then we have the LGM terminal moraines, the down valley recessional moraines, which we are calling all recessional moraines that occupy a position in the valley that represents a recession from the terminus of less than 25%. So these are all moraines that are positioned very closely to the terminus, to the terminal moraine, but do indicate some recession. And then the up valley recessional moraines indicate a recession from the terminal moraine of greater than 25%. So any moraine that lies within this broad green area highlighted in this example would be an up valley recessional moraine in our classification. And then subcirque moraines would lie on the cirque floor and represent that final push of these LGM moraines before the ice finally melted. So if we look at all of this data based on these, or divided up into these groups, we can use these violin plots and box plots to kind of assess the distribution. The violin plots give you a better visual, and then the box plots give you a bit more of a numerical view of the distribution. And then the red dots in each of these are the mean value. So for all of the terminal moraines in the Great Basin, which we have included Sierra Nevada data in, because it's kind of nice to include because there is so much data available, and it does respond similarly to data in the Great Basin. So the mean value for the terminal group is 19.9 with a standard deviation of 2.7 thousand years. And we can see that there is a pretty broad span in these ages, with a larger tail on the older end. A lot of ages in this tail to the older end may indicate that we have interrupted exposure histories or pre-depositional exposure. And that is something worth looking at. I know I looked at a couple just to remind myself before presenting, and many of the older ages have much larger uncertainties. So it's something that we need to be aware of when we're talking about all of this data. The down valley recessional moraines have a mean age of 16.9 thousand years with a standard deviation of 1.4. The up valley, a mean of 14.6 with a standard deviation of 1.6, and the subcirque, a mean of 13 with a standard deviation of 1.6 as well. So what we can see here is that our four groupings seem to make a lot of sense age-wise. So our down valley recessional moraines that are staying close to the terminal moraine, they all seem to agree pretty well in age, and they are across the Great Basin agreeing, and the same with the up valley and cirque age moraines. So when we look at these as ridgeline plots, which is the next slide, we can see the individual surfaces. We obviously have a lot more surfaces of terminal moraine age, and we have good agreement in the terminal ages, but upon discussing this after we made all of these graphs, we wondered if there were some moraines that have been classified as terminal or have been mapped as part of a terminal complex that may really represent a recessional moraine that should be included in our down valley recessional category, that represent this maintaining of a long ice extent for a longer period of time during this pluvial lake high stand. So this shaded column in the graph between 15 and 18,000 years ago represents the local pluvial high stand as a general band of time. So we can see these down valley recessional moraines fall pretty cleanly within that pluvial lake high stand of the Great Basin. So we're seeing that during the time when these lakes occupied their high stand shorelines, we're also seeing substantial glacial extents that show very little recession from their terminal moraine position. And then we have a movement forward in time into our up valley recessional moraines, which are generally forming after the end of this pluvial high stand period. and then again forward into our subcirc moraines. So we're going to look at each of these individually based on range. So first we'll look at the terminal age group. We have the most data in the Sierras and in the Ruby Mountains, with a lot in the Wasatch and the Uintas, and much less in the smaller ranges in the Central Great Basin and the Northwestern Great Basin. It would be really great to see more data in these smaller ranges, but there's just less work that has been done there, and less to be included in this analysis. So we can see that most of these terminal moraines formed before the pluvial lakes reached their high stand, with some exceptions. And this could, again, be a situation where moraines have been included in a terminal complex or been labeled as a terminal inner, but we should have grouped them in the down valley recessionals. But that's something that would need an individual checking. So when we look at a map, we can see that there could be some analysis done spatially. We see a more early response in the Sierras, which have a slightly different climatic dynamic, and then potentially a later response in the Uintas and the Wasatch. When we look at the down valley recessionals, which we have substantially less surfaces dated from, we see that they, again, very strongly agree with this pluvial lake high stand period, especially in the Santa Rosa and Ruby, where we have the most data, and then also in the Humboldt. You'll see we have a couple of spots, the circles on the Wasatch and Pine Forest lines. Those are age dates that we have for surfaces, but we have less than 4 dates, so we don't calculate any ridge lines for those surfaces. And then up valley surfaces, we have slightly more, mostly in the Ruby Mountains. That is where the most robust chronology is available in the Great Basin. Some in the Wasatch. Both indicate mostly that these up valley surfaces were forming after the pluvial lakes were at their high stand or fell from their high stand, and then a couple of surfaces from the Sierras. We have 3 subcirc surfaces, one from the Sierras, which again has slightly different climate dynamics, one from the South Snake and one from the Western Uinta. And these indicate that the glacial valleys in the Great Basin were ice-free by 11 to 12,000 years ago. I think the next thing, we're going to talk about are the pluvial lakes. So we did some closed basin modeling of the pluvial lakes based on a method from Condome et al. So this is a water balance model which uses precipitation and evaporation to compute a soil water capacity, or kappa S. And once you have the kappa S calculated, it is put back into the equation to solve for a series of temperature and precipitation values, which could have supported the lake elevation, the specific shoreline. So each of these shorelines, given as 1725 and 1830, are representatives of specific shoreline elevations from pluvial lakes Franklin and Clover. So pluvial lake Clover consistently resulted in predictions that were higher in precipitation and temperature than pluvial lake Franklin. And this is plotted against glacial modeling from glaciers in the Ruby and East Humboldt Mountains. And when we look at these ranges of ages, it's important to realize that we have to choose a range of years that is substantially larger than would be ideal, because we need to include data, include models from different locations that don't necessarily overlap in time perfectly. So we have three ranges: 20 to 19, 17 to 15, and 13 to 11,000 years ago. And these are different combinations of models based on three different glaciers and two different pluvial lakes. So from 20 to 19,000 years ago, these suggest an overall temperature depression of 10 to 11.5 degrees C, and no real change in temperature or no real change in precipitation. The range varies from 0.6 to 1.3 times modern precipitation. Between 15 and 17,000 years ago, this gives us an approximation or a range of temperature depression between 7.5 and 10 degrees C, and a precipitation factor between 8 and 1.5 times modern. So again, no significant change from modern precipitation. The only time we see an increase in precipitation from these models is from 11 to 13,000 years ago, which would indicate a change or an increase in modern precipitation by 1.3 to 1.7 times modern. This also indicates that at this time there would be a temperature depression of 5.5 to 7 degrees C. So these are pretty significant temperature depressions that seem to be driven down, especially in the older two ranges, by the modeling of Lake Franklin. So there's something interesting going on there for sure. Bellinger also did a similar calculation with glaciers in the Wasatch and Lakes Provo and Bonneville, and found substantially lower temperature depressions were predicted and higher precipitations, at least for the periods that he was studying. So when we plot all of these together, the modeling from the Wasatch and Bonneville set of data show a much lower temperature depression. So at 21,000 years ago, here in red, it would only have been a temperature depression between 9 and 10 degrees, while the modeling from Lakes Clover and Franklin suggested a temperature depression between 10 and 12 degrees. So Lakes Clover and Franklin resulted in a much broader range of possible temperature and precipitation conditions. And this was in part based on the way that the models were, the comparison was set up, because we used a wider age range of glacial and lake models, mostly because because of the ages of models available. So I believe that is all I have for you to conclude. This inner range comparison shows that these groups, based on moraine location, were broadly synchronous throughout the Great Basin. The separation of recessional moraines between up valley and down valley seemed to be a useful way to divide the two, and showed interesting alignment with the pluvial high stand period. Glaciers remained near their terminal extents throughout this high stand period, and up valley recessional moraines were generally deposited after this period. And then glacial valleys were generally ice-free by around 12,000 years ago. I think that's all I've got.
All right, thank you, Jordan.
You.
We do have plenty of time for questions here, and I see Jeff Monroe has his hand raised. Go ahead, Jeff.
Thanks, Ben. Thank you, Jordan. God, it's just so cool to see these compilations, and we could just stare at these and talk about these all day. The ages in particular, so much there. I'm curious, I like the way you're grouping the moraines and the moraine ages to try to make some sense out of it. And I could certainly be convinced that like the terminal moraines and those down valley recessionals, I guess I'd say they likely are driven by some kind of climatic event, particularly given the synchrony with the lake high stands. But what do you make of the up valley recessionals? If there's convergence in those ages, is that dumb luck, or is that some kind of later climatic forcing, or is that are those all individually driven by just the unique hypsometry of those different valleys? Tough question to answer, I know, but I'd love to hear your thoughts.
Yeah, I would say that it's hard to make any statements about the up valley recessionals, especially because we're so limited in the surfaces that we have dated. Almost all of them are from the Ruby Mountains. So any statements we would make would just essentially be about the rubies. Yeah, I'm not sure on broader implications just because we really don't have that much data available.
All right. Dan has his hand raised. Go ahead, Dan.
Hi, Jordan. Thanks. That was really great. So I'm interested in the Northwest Great Basin, and I guess I have two questions. One is, what's this glacier that's sitting northwest of Lake Alvord? It's the Steens Mountain that's basically behind the word forest on your map here.
Yeah, I'm seeing.
Is there any chance that we'll be able to get a record out of there to compare with these Northwest Great Basin lakes? And then additionally, sort of modeling of pine forests in Santa Rosa, because we have such great, high stand constraints on Lahontan and some of the other lakes that I work on in the Northwest.
That would be awesome to include. I'm sure that there is more data that is not included in this, and I would love to gather any other data that is out there. And then lake modeling in the Northwest would be great. I know Lakes Franklin and Clover are more central. So having something up in the farther Northwest portion of the Great Basin would be a great thing to include.
Go ahead, Joe.
Jordan, thank you for a really awesome talk. Would echo what's been said already. We can stare at these ages and talk about them for a long time. I just want to jump in and also say that about the Steens, to Dan's question, I actually did field work there long ago, and there's some really nice deposits there that are amenable to dating. Our original idea was to do helium, but we were pretty sparse with the olivine and pyroxene, so it looking like it might be chlorine, but certainly a lot of potential there. And we've also been working with those glaciers using the glare tool, or at least starting to do that. So I agree, extending some of these up into the northwest part of the Great Basin would be super interesting, but there's so much data that you have to work with further south. It's just amazing to see. And thanks again for a great talk.
Thank you. And yeah, thank you for mentioning the glare tools, because all of the modeling of the glaciers was done before the glare tools were available. And I wasn't a part of doing the glacial modeling that was included in the Lakes Clover and Franklin portion. But the availability of the glare tools and other tools would really make it more accessible to expand this across the Great Basin.
All right, well, we still have a little bit of time left here. Have any more questions for Jordan or any follow-up?
Jordan, I have a question for you, more of just maybe a discussion topic. So I've been focused in on the Pioneer Mountains in Southwest Montana the last few years, and comparing to a lot of the work that Joe Licciardi has done in the greater Yellowstone area, and also sort of thinking about regions proximal to the Laurentide ice sheet and sort of how they might be different than the Great Basin region.
Right.
I've been curious about how, much like the Wind Rivers and the Bighorn Mountains, and sort of the northeast part of the Beartooths with, say, Clark Canyon, they're coming in, early, like in the 21 to 22K time period, which sort of really follows insulation changes. Like if we follow the insulation curve, they're really responding to insulation. But it looked like a lot of your data is later, the 19.9 plus or minus, I think it was 2.7. And you'd also sort of highlighted that some of those younger ages might actually be either terminal moraine complexes sort of mixed in with the maximum ages, or maybe they're real LGM ages. So I'm just curious, as we look at the spatial variation of sort of like pretty early changes close to, or not necessarily close to, but northern in Wyoming, and then sort of a little bit later down in the Uintas, or not the Uintas, but the whole Great Basin area, sort of have a period there of change. And then it's sort of like delayed later than the insulation changes, but not, the pluvial lakes aren't there yet. So what do you think might be driving that delayed response, delayed relative to insulation?
That is an interesting question, and I don't know if I am fully equipped to answer it, but I do think that there are other climate dynamics that really need to be delved into. I don't think that I have an answer there.
Well, I can just offer a little insight from our Montana data, which still needs to be calibrated to the promontory point production rate. We're just using the LSDN scaling right now, but it appears, at least in the Pioneer Mountains, that we have our maximum ages around 18.5, 18.7.
Okay.
And it's interesting because it's different than the Wind Rivers and the Bighorns. It's similar, but a little bit older than the Greater Yellowstone ages from like Chico and sort of the Northwest Greater Yellowstone Glacier system that's closer to us. And I had proposed, and I've been talking with Caleb about this, Caleb Walcott, about the proglacial lakes out in front of the Laurentide ice sheet margin as maybe a potential moisture source delaying our retreat. And so we're curious about that because of your pluvial lake work that's been done all down in the Uintas, sort of how that affected the timing of retreat through the Uintas and sort of extended the Western Uintas. I'm thinking that there might be a similar process going on in the Greater Yellowstone and Southwest Montana, that there's huge lakes, Glacial Lake, Great Falls, Glacial Lake, Missoula, and then these big katabatic winds that are actually coming out of the northeast rather than our current prevailing westerlies. So it's sort of a whole mind shift in thinking about where is the moisture source coming from close to the ice sheet. So that's just some food for thought, I guess.
Yeah, that's very interesting. And that might be something that Dr. Lobbs could speak to a little bit. I know that he has thought about the pluvial lakes a lot and different moisture sources within the Great Basin. Myself less so, but that is definitely a very interesting vein of questioning.
I would just add real quickly to that we've learned about some chronologies so far, and we're going to learn more as we hear from Aaron in just a minute here. But these down valley recessionals are, on this slide that Jordan is showing here, we have a bunch of these in some places and just a handful of them in other places around the Great Basin, and that's through a lot of mountain ranges. My argument would be that we don't have enough, and that's just kind of the way that the cosmogenic dating has worked on moraines in the West. People have gone out to terminal moraines and looked across all these different mountain ranges. People then went up to cirque floors and looked across a bunch of different mountain ranges. And I think we're just starting to look at the space between a little bit. But one of the models that I think we should maybe try to consider as well is just starting with the glacial record. And Joe Licciardi's work, I think, was really good at taking that approach, identifying these different glacial episodes, Pinedale 1, Pinedale 2, and so on for the Rocky Mountains. And we can take a similar approach elsewhere, and Brendan Quirk has started to do that. And once we have that broader regional view, we can see just how common some of these younger moraine ages are, post 21K, post 19K, because I think they are becoming more and more abundant, not just in the Great Basin, but in other places too. And then I think we've got an opportunity to not just start looking at paleoclimate, but just to get a better classification of these, of the scope of these different glacial episodes. So, I hope we can keep talking about this. I think for now we should probably move on to Aaron's talk. So there's Aaron. Okay. Sorry, my tiles are really small on my laptop, so I just wanted to make sure you were still here. All right.
Yep.
Great. Well, thank you again, Jordan. And we'll move on to Aaron, who is an assistant professor at Rowan University in New Jersey, and had to fight through some traffic to get here for today's seminar. So we're glad that Aaron's here. Aaron's originally from the Washington, D.C. area. He earned a PhD at Oregon State, working with Peter Clark, and he's worked as a postdoc with Sean Marcotte at the University of Wisconsin before moving out to Rowan. So he's back east, and he's doing some work on glacial chronologies in the West, and also doing some surface exposure dating in the Adirondacks. We're going to hear about the West today, specifically Montana. So why don't you take it away, Aaron?
Great, thank you. Let me see. Oops, I'm giving away a little bit here. Let me go back to my title slide. All right. And can everybody see that all right?
Yep.
Great, thank you. All right, well, yeah, thank you very much for having me first be a part of this working group. I love learning about everything that's everybody's doing in the West and kind of the commonalities behind it all. And it's a exciting opportunity for me to talk about some work that I've done with my colleagues here and how we kind of fit in our role within this larger group that we've been talking about for the last few weeks. And I couldn't be more excited too, because that last question set me up perfectly, because I'm going to touch on exactly that thing in just a minute. Now, admittedly, when we get there, you'll find out that I'm going a little bit out on a limb. So hopefully you'll, bear with me a little bit when I get to the interpretation, but I think it's going to feed right into that conversation. And what I'll talk about today is some data that my colleagues that you see listed here and myself collected from the Beartooth Mountain Range in southwestern Montana, or southern Montana and northern Wyoming, and particularly from the Rock Creek Basin, that there were some previous studies by Graff in 1971 that went through kind of geomorphic interpretations of what these features meant. And so we wanted to go back out and add to that understanding. And I'm sure we're all familiar with this figure here on the right from Ben's paper in 2020, but it's worth mentioning the motivation behind this that I'm sure we can all agree with. But there's this great growing compilation of data that we're gathering from the Western US that's really getting us to better appreciate the variability and the shared signals that we're seeing regionally across this entire region. And we just wanted to add to that by starting to fill in maybe some gaps or add to some spaces between existing data and see what we could come up with. Additionally, we wanted to continue to build on this hypothesis testing that we saw with Sean Marcotte's paper in 2019, where we were looking at these really cirque proximal deposits that have originally been interpreted as late Holocene, maybe neoglacial. And this figure in the bottom left from that paper shows the pink, the original interpretation of what the age of those deposits were versus what they turned out to be using surface exposure dating from Sean's paper. And the idea that what were initially thought to be these young late Holocene deposits were in fact latest Pleistocene. So we wanted to go out and add to that, test this particular valley, and see what we can find there. So to give you a little bit of background of where we are, this is in the Rock Creek drainage, which extends out of the northeast corner of the Beartooth Mountains. So if you look over here on the right, and sorry, all your faces are covering my map on my view. So if you look over here on the right, this is the northeastern corner of the greater Yellowstone system with the Beartooth Range right here. And this valley, if you can see my mouse right here, that's the Rock Creek drainage really coming out of the top right corner of that range. And down here in the middle is the town of Red Lodge. And in 1971, Graf went out there and mapped a whole series of moraines, including these terminal ones that wrapped around the town, and a series of recessional moraines that, using Jordan's terminology, we have our down valley recessional moraines along with some upper valley and some cirque proximal moraines that then, based on geomorphological characteristics like profile and soil regression, but soil, sorry, my mind's gone blank. Soil profiles, they assigned certain ages, whether they're Bull Lake or Pinedale, and he assumed that the terminal moraines around Red Lodge were Bull Lake in age, and that everything in the lower valley that we say is, let me go ahead and put on I don't know where that is. This valley down here, that's the lower valley, and everything in there was Pinedale. And then these really cirque proximal moraines, he determined all to be late Holocene. So this is a nice view looking on this kind of lip that's this transition between the upper valley, as we refer to it, down into the lower valley where these Pinedale hypothesized recessional moraines existed. And the way we approach this is we got funding to go out and collect a handful of ages for surface exposure dating using beryllium-10. And we targeted 4 moraines that were previously mapped as neoglacial. 3 of those were cirque proximal, so within 1 kilometer of the head wall, including these around Little Glacier Lake, which we see here. So this is the Little Glacier Lake moraine right here, along with Triangle Lake, which is this one right here, which is just about a couple kilometers to the west of Little Glacier Lake. And additionally, there was another moraine, the Emerald Lake moraine, that was the most down valley within the upper valley, or the stratigraphically oldest moraine within that late Holocene hypothesized deposit. And we went out there and we collected a handful of boulder samples that we then dated for beryllium-10, using beryllium-10 back at the University of Wisconsin. And what we found, so just getting into the ages, was that if you look at Emerald Lake in particular, and here's a map of our site looking down on it, this is the Triangle Lake cirque, here's the Little Glacier Lake cirque, and then this is the Emerald Lake moraine right here, is that the Emerald Lake moraine ended up yielding ages between 11 and 13,000 years ago, with a mean age of about 12.5. So in terms of being Holocene, we can rule that out. We can say this really falls nicely in the late Pleistocene, and we'll talk about the implications for that in a minute. But these other ones, these other 3 moraines that were more cirque proximal, those did come back as late Holocene, getting ages somewhere from about 2,000 years ago to as recent as 120 years ago for the one around Triangle Lake. And here you can see an example of some of the boulders we collected, just to show that these are large features. So if you're interested in any kind of geologic uncertainty like exhumation or erosion, we followed all those strict sampling protocol and criteria to make sure that we got as accurate an age as we could. But the key here is that the Emerald Lake moraine in particular came back to be much older than this late Holocene, while these 3 other moraines that were much closer to the Zerk did absolutely fall within that boundary, although with some admitted spread within the ages. However, ignoring our data for the moment, I want to talk a little bit about the last glacial maximum and some potential interpretations of the glacial deposits there. And this is where I'm willing to go a little bit out on a limb, so I hope you bear with me. But if we look at this figure here, we've got age going from oldest to youngest on the X, so from left to right. where we have in the top here in the blue, the ages of the different moraines that we collected from this study. And then in the black, 3 more proximal to our study site ages from Pine Creek, Crandall Creek, and from Clark's Fork. And additionally, here's a curve of of temperature taken from the Osmond et al. 2021 paper for our study area, along with insolation down here in the orange. And what I wanted to talk about was the idea that if you look at some of the studies, including those by Jeremy Shacken and by Nicholas Young, they suggest that Western glacial retreat effectively started sometime between 22 and 18,000 years ago. And that's shown here by the yellow bar on the left. And if you look at some of these ages from the proximal moraines, terminal moraines to our study area, like Clark's Fork, they fall within that boundary, with Clark's Fork coming back as 1908 and Pine Creek, which is to the west, coming back as about 1802. So while it was interpreted as Bull Lake from Graff in 1971, we hypothesized that the terminal moraines around Red Lodge, in fact, represent a LGM deposit, which is similar to what we see across the greater Yellowstone glacial system. And if you look at characteristics in terms of morphology, and the fact that this is the terminal position, that there are no deposits outside of these margins, we think this is a decently supported hypothesis. What I want to talk about next kind of fits into the end discussion that we were just listening to between Jordan and Spruce, is the idea that if you look at the age of the Clark's Fork moraine in particular, that started about 1908 based on the Cosmo ages from there, and that we saw rapid retreat from that, where it went up valley to the Crandall Creek moraine, which was then deposited, or at least you have moraine abandonment about 18.2. And Joe can confirm this or not, but I think you saw about 40 kilometers of retreat over that very short interval. And at the time, I think this was attributed to the formation of a rain shadow as the ice cap on the greater Yellowstone system started to pull back and closer to the southwest, therefore starving the Clark's Fork Glacier of precipitation. However, if you look at the Pine Creek moraine, which is just to the west and again morphologically similar to those around Red Lodge, that didn't start to retreat until about 18.2 thousand years ago, similar again in age to that of the Crandall Creek moraine. What we are suggesting now is that based on this window of time from about 22 to 18,000 years ago, when Western US glaciers were supposedly retreating from the LGM margin, that based on the Clark's Fork moraine and the Pine Creek moraine, that maybe ours around Rock Creek had a response later in this time period. And that's also based on the idea that after Clark's Fork retreated up to the Crandall Creek boundary, you see this construction of a series of recessional moraines after that 18.2 time period, similar to those that we see in the lower valley of the Rock Creek drainage. And that this continued recession of the moraines or of the glacier after this 18.2 margin, where it slowed down a little bit, continued until we have construction of the Emerald Lake moraine, or leaving the lower valley about 12,000 years ago. And I know this again goes out on a limb a little bit, but if we're willing to accept mean retreat rates, if you use the uncertainties and this time window, we can say that we have retreat of the Rock Creek Glacier, a minimum rate of retreat of about 2.8 meters per year and a maximum rate of about 4.9. Whereas if you look at the Clark's Fork moraine, that 19 to 18,000 year window, you're looking at a mean retreat rate of about 28 meters per year. So drastically faster. So this is something I got into, but just this idea that what we think happened, and I'd love to discuss further with people, is that we're seeing this rain shadow effect maybe affecting the eastern portion of the greater Yellowstone glacial system, where we have rapid retreat of the glacier about 19.8 thousand years ago, somewhat stabilization prior to 18, and then a more gradual retreat almost synchronous from Clark's Fork, from Pine Creek, and maybe from the Rock Creek boundary after 18. And this could be a product of the northern portion being fed by those pluvial lakes that we just discussed. And I think, if we want to get into that in a little bit, that'd be fantastic. Talking about more substantial, or substantiated, I should say, interpretations of our data. If we look now at this age of the Emerald Lake moraine, this falls nicely within that window of time that could be interpreted as Younger Dryas. And what we think this could suggest is that we had stabilization of the glacier prior to this age in response to the Younger Dryas cooling. And what we think is most interesting about this is that if we look at this probability distribution down here at the bottom, this is a compilation of some Younger Dryas age moraines from the Western US, taken from some of Joe's work and some of Sean's work, including this one. And what we find is that you get a window of about 9 ages that fall between this 12.9 to about 11.5 thousand years ago window. And we think this suggests that you potentially had a regional response to the Younger Dryas cooling. However, you do see this wide range in ages that potentially there's this variability into the onset of retreat from that response. And that could be due to a series of things, including changes in precipitation, changes in lapse rate, or maybe even topographic effects. That you get some local variability leading to changes in the timing of retreat from that Younger Dryas response. However, it's worth admitting that based on the uncertainty of these ages, we can't say in particular that one age is early Younger Dryas versus one is younger or later in the Younger Dryas. There's too much uncertainty for us to say specifically. We just like that hypothesis and wanted to put it out there. If we move forward in time to these younger ages, we see that around Little Glacier Lake, for the right lateral moraine, we get ages ranging from about 720 to 2,000 years ago. And for the left lateral moraine, between 10 and 2,000 years ago. Well, 1,000 and 2,000 years ago. And admittedly, if you look at the ages here on the right, we get a decent amount of spread with not enough uncertainty to have overlap within those ages. And we think that this is potentially a problem associated with rock glaciation for this particular location. If you look at the morphology of it, it's got a really steep toe to it. It's very bouldery. And then within the middle, there's some ribbing amongst the fairly flat deposits. And it seems like there might be some amount of rock glaciation affecting that. For that reason, we thought, well, based on some helpful reviews from our reviewers, that it's safer to interpret these not as a mean age for these, but as a range, and then use that as a closest limiting approximation of when glaciation initiated and when it left. Additionally, if you look around Triangle Lake, we've got ages running from about 120 years ago to 390 years ago, again with a decent spread. But we think this interpreted as that age of or glaciation persisted within this region until about 120 years ago at the latest. And seeing how this fits into the larger regional picture, now looking at, again, age on the left going from older to younger on the right. Here we've got up at the top our different ages presented as those ranges, with the 2 from Little Glacier Lake and the 4 ages from Triangle Lake. And then here we have some lacustrine records from Jeff Monroe's work from Glacial National Park, where we suggest that the shaded areas under the curve are indicative of favorable glaciation or active glaciation, and as opposed to the time periods below the shaded areas where there was not. And what this suggests to us is that there were conditions favorable for glaciation, but then variability within that. Then maybe you had some migration of the margin, although minor, within that time window. Therefore, our interpretation of the data as a whole, and which is we're happy to discuss and to test later, is that you potentially had climatic conditions favorable for glaciation by about 2,000 years ago, or the earliest ages, and that persisted until we have the youngest age, where the glaciers left that margin as late as 120 years ago. So just to kind of wrap it up, we went to the Beartooth Mountains and we wanted to add to this data set of growing Western United States glacial records. We now feel pretty confident that at least the Emerald Lake moraine is representative of latest Pleistocene glaciation and not late Holocene. However, we do see evidence of late Holocene glaciation, potentially suggesting climatic conditions favorable for neoglaciation by about 2,000 years ago, if not earlier, that persisted until the end of the Little Ice Age. And I'll leave it there and happy to talk about any more.
All right, great. Thank you for that, Aaron. Questions for Aaron or a discussion? Go ahead, Joe.
Aaron, great talk. Thank you for that. A lot of really interesting things to think about. Yeah, I would love to talk more about the ages you're getting and how they might fit in with the pattern we see from the Clark's Fork to the Crandall Creek and how that compares to Pine Creek. But so the Pine Creek moraine is a terminal moraine, and we didn't really identify any recessionals up valley from there, but there are ages on the bedrock, which you might know. Those were published by Brendan Quirk, and that was actually work by Liz Huss, who was working with Ben at the time. And in that paper, there is a retreat rate. Ben, I don't remember if you know the number there, but it would be interesting to compare that rate to what you're seeing in your valleys in the easternmost Beartooth uplift. Have you done that, or have you considered that at all?
No, I haven't looked at that retreat rate, but I think that's what I would love to get into next. Kind of my vision of how to keep expanding upon this work is to, one, collect more data, but I'd love to look at what I'm most interested in is seeing the variability between valleys that are near each other. Is it going to be a consistent climatic signal that's driving this consistent synchronous retreat, whether the valleys are next to each other or whatever? Or do we see this variability? And I think that'll play in not just to the timing, but then also into the rate of retreat. And I think, if we can do that in a comparison, admittedly, we're doing this based on just a hypothesis of what we think those terminal moraines are. And I think we talked about this last year, that you have plans to actually go out and date those moraines, which I'm all for, because I think that's going to just help us immensely. But that's kind of my idea, is I want to go out to different valleys. I know I've been thinking about some in Idaho, up in the Sawtooth Range, where there's an opportunity to get some really nice terminal moraines and then follow those all the way up valley to the circ proximal position and see what we can start to say about mean retreat rate from one valley and then one right next to it. And what's the comparison? And think about how much these local effects are having a control.
Yeah, I agree. And it sort of gets back to what Ben said in a comment earlier, that the middle parts of these valleys have been understudied, with so many of the earlier studies just going after the terminals and not going for full sequences. So I absolutely agree with that, with the comment that more of that type of work needs to be done.
Yep. Yeah, thanks.
Jeff, go ahead.
Thanks, Aaron. God, this is great. I love these studies that actually have ages that span like the whole range of what's there, kind of a theme for the afternoon. So just a kind of a specific question. I didn't think of it quick enough when your slide showing the results from, I think it was Little Glacial Lake was up, and you said that it might be rock glaciation here. And then I wanted to see the data again and see if there was a spatial pattern that would be consistent with, older boulders down valley or something. And I guess yes and no, huh?
Yes and no. It was a pretty messy data set. And I wanted there to be a consistent signal between them, but no, there just wasn't. So
Should
that's
have
why
only done the right lateral side. It would have
I
looked
should
good.
just stop there, right? get data that fits your story and then stop collecting. But it was funny. I presented this at GSA also, and if you look at our one outlier from Triangle Lake, it kind of falls nicely in that 2,000-year-old story. That we're also getting a little glacial lake, and somebody made the comment, do you think that could be representative of a 2,000-year event, in that you're actually seeing that, and then maybe a 700-year event, and then maybe like a younger event from that? And I think that's absolutely possible. If you actually squint your eyes a little bit and look down here at Triangle Lake, there's a terminal position, and then you've got all these little potential recessional moraines that exist just north of that. And where we are out here on the edge, it's possible that we were collecting deposits from a younger aspect here, and that this one, the oldest one, is the most down valley one, that maybe that was part of an older event there. And while we do have boulders from there that we never processed, we ran out of funding. So it's just, we picked the ones that best fit our selection criteria and went with those.
No, it makes complete sense. Isn't this such a great example of how, I guess it's just in geology in general, like we strive to ask these more specific questions in the parts of the record where we have more data, which are usually the parts that are younger. So like here, right, you're getting worked up about like ages that are 100 years off one another, and then for the younger Dryas, you're like, why do they spread across 1,000 years? Does that mean something? And then we look at Jordan's data, and we're all completely nonplussed by 20,000 plus or minus 2,000 because that just sounds fine. Like it's, I don't know. I've always found that interesting and always worth like checking ourselves on that tendency.
Right. And especially as somebody who spent most of my work in kind of later, early deglacial stuff, to get ages coming back with an uncertainty of 10 years, you'd think I'd be really excited about that, but then it doesn't help me with any kind of overlap.
Yeah, remarkable. Well, great stuff. Thanks so much.
Thanks.
Any more questions or discussion for Aaron? Bruce, I can see you waving. Go ahead.
Well, I want to make sure other folks get a chance to chime in if they have questions, since I already spent some time. Is there anyone else who needs to run off and wants to squeak in a question? All right, I'm gonna go back to the conversation that you had brought up about the Rock Creek ages, and it sounds like Joe's gonna go back there and actually get some of these Pinedale ages from terminal moraines. I really curious to see how that plays out, if it ends up being more like Pine Creek versus the Clark Fork. It would seem to be similar in location. It's sort of northeast Beartooth front. It's not that far away. And I would sort of imagine that whole northeast corner would somewhat behave similarly if it's in either the rain shadow area concept, right? So the orographic precipitation migrating southwestward through time. So it might end up being more similar to Clark's Fork, but my one thought was, I've spent quite a bit of time doing field geology in Red Lodge. I did my field camp at YRBA, and then I actually taught for YRBA a few summers ago. And there's some really interesting glacial landforms there that I suspect was probably a Piedmont glacier. From my field mapping that I did, a very large Piedmont that sort of wraps up towards the ski area, which is out in the Beartooth front. It wraps up over a couple of knolls that have beautiful homes on them. Like on these tops of these beautiful knolls, you have this sort of a trim line of, it's not a trim line, it's a deposit of till, but I have no idea how old any of it is. And I kept thinking the same thing. Joe, you're probably thinking that it's a very unusual area for some rich research, and it would fill in that big gap. So as well as, I don't know if you've thought about going down to the Rosebud a little bit further to the west, as well as Rock Creek. Those two would just be stellar. And I think you've mapped, at least in one of your papers, it looks like there's a little bit of Bull Lake mapped like out in front of Rosebud, or I think it's East Rosebud, but I'm very curious about that.
So I can sort of speak to that. Though first of all, I would say I think that my prediction is that all of the prominent terminal moraines coming out of those canyons are likely to be Pinedale. The Bull Lake is on the map because that's based on earlier mapping that has not been double checked with more modern dating techniques. That was based on relative dating. And the Rosebud and also the Stillwater drainages, those are the targets we have in mind. I've seen the Red Lodge moraines, maybe not the specific ones that you mapped, but there's a lot more development there, and it seems a little bit more challenging. And I know that that Sean Marcotte had gone out there as well to be looking at some of these deposits for scouting purposes. But in any case, my prediction would be that we're not going to find much Bull Lake out there unless it's out in the form of terraces and outwash. But that's a testable hypothesis.
Yeah, well, when you guys do get the funding, go out there, I'd love to just tag along. It's so close to where I work, and I'd love to just be involved in terms of an asset on the ground, hammering and chiseling.
That'd be great.
Yeah. Yeah, I forgot to add, I love the circ work that you've done, just sort of differentiating between the latest Pleistocene and then late Holocene. It's just amazing. It's something I'd like to do in our region over in the Pioneers and some of the other big valleys. But yeah, the money is one of those key challenges, time and money. Yeah.
Right. Well, I think that really feeds into what Joe and I were talking about too. It's just like, and it came up during Jordan's talk too, is that our understanding of this declacial recessional story and how consistent it might be and how variable it might be, we don't really know. And it's something, if we can just go out and get more ages, more data, more mapping, I think it's just going to really benefit all of us. And I know
hopefully I'll have some more for you also on the Bitterroots in Montana. We're getting some great ages out of there. So hopefully we'll have a neat chronology story for the Bitterroot Mountains by next spring GSA.
Great.
So more to add. And
that's great. And I know we're just about out of time, but I love pointing this out to people who know. Looking at this probability distribution, is that this stands out to me, is that that was a date of the 4th of July moraine that came out of Sean's paper that I helped process those samples where I was teaching an undergraduate to do the samples. And it's the best damn data set I've ever seen in my life. And it was the one that she did, and she never did it again. It came back like, I can't remember the exact age, but it was like 12.5 plus or minus 0.2 for all of them except one. There was like 12.4 plus or minus 0.2. And it just makes the probability distribution look ridiculous.
Where's that student now? We need to get them back.
Yeah, she went and got her master's from South Dakota School of Mines in hydrology, and then that's it. But she's it's Claire, so the third author on this paper, because she helped me process all these. So there she is. Yeah, and never did it again.
Like buying a single lottery ticket or something.
Right, right.
Yeah, going out on top instead of we just keep hammering away at things, and our data just gets messier and messier.
Right.
All right. Well, we've passed the top of the hour here, so I think we can sign off at this point. Thanks again, Aaron. Thanks everyone for contributing to the discussion. Thank you, Jordan. And we've got a lot of chronology to think about. We'll hear more about this. Next week we have just one speaker on the schedule. That's Joe Tulenko. Joe's going to be talking about the Alaska Paleoglacier Atlas, but may do some talking about ICE-D as well, that informal cosmogenic exposure age database where a lot of our data are ending up, and nicely represented, convenient formats. So we'll keep these ideas and these conversations going for sure. Next week we're back on Friday again, so I'll send a reminder about that. And if you're here and you're looking for any talks that you might have missed, I am including YouTube links to the recordings that we've made so far. You can go to the working group website, which if you do just a Google search on Western U.S. Paleoglaciers or something like that, hopefully that's starting to show up as one of the top hits. So thanks again to everybody, and we will see you next week.